Okay, so lecture 16 is transformers. So this was actually a part of three lectures in a row. So this is the first part of that. So we are going to talk about multimodal learning from today. And multimodal learning is where we are going to define what is multimodal learning in the next lecture. So we're basically dealing with multiple modes like image, video, sound, text, or more. So what we can do with those different types of data set and how we can learn something useful out of them. So basically, that's the main question in the multimodal learning. And these days, the transformer is the most widely used tools for, especially in the NLP, nowadays, even in the computer vision. So today, we are going to cover the basics of the word embeddings in the transformer and its state-of-the-art word embedding model, which is BERT. So probably we are going to deal with only this part today. And in the next lecture, we are going to cover some transformer-based recent image video classification. This is new in this semester because some of these papers were not even published in the last semester. So this part is only available in this semester. And then we are going to talk about multimodal representation learning in lecture 17, and followed by image video captioning in the next lecture. So this part is slightly shorter. So we're going to cover like these three lectures in the next three or four classes. So introduction to the word embeddings. If you have taken natural language processing courses, probably you're familiar with most of these. I'm going to just very briefly talk about what are the word embeddings and what ideas were proposed there, because this is a computer vision course, and I'm not an expert in NLP, but just the basics you need to understand to follow the multimodal modeling. So word embedding is basically embedding the word in a vector. So far, we have embedded all the images, image in vector, and we use those vectors to like classify or segmentation or all the computer vision tasks. We have used vector from the image or the video. So in natural language, it's the same. Word or sentence or even paragraph, all of them can be represented in a vector, preserving their semantics as much as possible. So in a d-dimensional Euclidean space, a word is represented as a vector, and our goal is each vector actually needs to preserve their semantics as much as possible, something like this. Some words like expect is represented like this vector, and each of these words will be appearing in some n-dimensional space. So that's word embedding. And at the beginning of this line of research, Word2Vec and the Globe was the pioneer of this area. So this was from 2013, quite a long time ago, almost 10 years ago. So what they have done is using very large corpus, here the corpus is the collection of the text data, predict the current word from its neighboring words, or the opposite, predict the surrounding words given the current ones. So they trained just this model because it's really hard, easy to create training examples from this corpus. You have just picked one sentence and make one of those words as a blank, and then train some classifiers that all the surrounding words nearby that blank is the input, and then you estimate the probability of all the candidate words in that blank to maximize the probability of the real word actually hidden there. So in that way, you can just create almost infinite number of examples, the questions, and then the model is just trained to complete the sentence with that blank. So basically, the formula is like this. They maximize the likelihood of this function. So given some word WT, then the probability of the surrounding words, which is actually this one, the second problem, skipgram question here. So this is the hidden word, and given that, what is the probability of that? Sorry, this is the known words, and these all other surrounding words are hidden here. And then what's the probability of each word here given that this is into, then the model needs to learn the probability of potential words here. Then yeah, it will get to know what kind of words can be here and what kinds can't. And yeah, based on that, they can learn the relationship between the words. And the GLOV, or the global vectors, is another type of the traditional word embedding. So they took into account the ratio of the co-occurrence probabilities. So this is their observation. So given the ice is there, the probability of these four words, like solid, gas, water, fashion, is like that. And if the given word is steam, then its conditional probability is changing like that. And then we divide this by this, then we see that some irrelevant words like water or fashion, the ratio is close to 1. But because the ice is solid and the steam is gas, so given ice, the solid is more likely to be appearing there than steam. Given the steam. So it's like 9 times larger, and this is much smaller. So something like that. From that observation, they have it's this loss function. So here they would like to learn the word embedding for 2 words, word I and J, and their goal was their inner products is similar to the log of the probability, the conditional probability of observing I given observing the J. So word embedding I is for this word, and word embedding J is for this word. And this tilde is added here because this is not symmetric. If the Pj given I will be different, but this inner products, actually, they can exchange it to each other. So they can actually learn different embeddings for their roar given in this conditional probability, or separate them. But more as general as possible, actually, they learn separate embeddings depending on their roar in this probability distribution, and then they take the average in the end. So anyway, their goal was in high level, the word embedding needs the similarity between the 2 word embeddings is approximated to the probability, the conditional probability of one is observed given the other is observed. So now you see that these bias factors can be absorbed to this W, as we have seen in the very beginning of our class. So you can just ignore this part. And then now this part needs to be close to this because they are applying some squared loss. So that's how they implemented this idea into this objective function. And then what is this? This is some weighting function to control overweighting for 2 rare or 2 frequent words. So for the details, you can actually look at the paper. I'm not going to cover how actually they control how much. That is too much details in this class. But anyway, the high-level idea is modeling the relationship between 2 words or the pairs to embed those words in some vector space such that their semantics is preserved like this. So it was really interesting observation that these are the pair of words, the same word, but one for male and the other for female. Something like man and woman is like this. They are the same thing, but one word is for male and the other is for female. And a very similar relationship is observed between the vectors of brother and sister, which means from the vector of brother minus man plus woman, then we have a vector of sister closely. So this actually shows that this GLOV vector actually preserves relationship between 2 words quite in a nice way. It somehow kind of understands the difference between man and woman, and the relationship between those 2 are actually very similar to the relationship between brother and sister, or uncle and aunt, or what else, like king and queen, something like that. So that's it. In a nutshell, word is embedded as a vector. That's it. We don't know how. You can learn that in natural language course. But we are going to learn about transformer now, which is kind of state-of-the-art in natural language processing, and also is widely used in computer vision these days, really recently. So we are going to learn more about the transformer in detail in this class. So what is transformer? It's basically multi-headed self-attention. So this is the summary of the transformer. Multi-headed self-attention. We learned about attention in lecture 14. So this is an extension from that model. Okay, so it was originally proposed in machine translation, translating one language to another, like English to French. And recently, the transformer is really widely used for NLP problems and even in the computer vision problems. So we are going to learn about 9 steps. And actually, yeah, let's start with the first step. The input is a sequence of tokens. So the token can be many things, but here you just think that it's a word, because we are going to use the natural language example until we're talking about the basics of the transformer. So each token is a word. So the input is a sentence, so which is a sequence of tokens or sequence of words. And then each of them is represented as some pre-trained word embeddings, something like glove, what we've just seen. So far, so good. Okay, so this input embedding is going to this box, which is the transformer encoder. So we are going to talk about transformer encoder from now on, which it takes the sentence or the sequence of tokens, and it will encode somehow. So let's see how. We talked about attention before. In attention, what was the key 3 things? Query, key, and value. We talked about that, right? It's really important to figure out what is the query and what is the key and what is the value. And that was the most important thing to understand the algorithm based on the attentions. Here's the same. We're going to talk about the query, key, and value, but we call this self-attention. So why we have the self here? So given the input, which is this X, suppose this is a sentence of 2 words, come here, something like that. So the first word come is embedded with these 4 values, so vector of size 4. And here is another word vector with this size 4. So this X is the original input. And we multiply some linear matrix, just linearly multiply some matrix to map this to query, key, and value, which basically just maps the original embedding to its query embedding, key embedding, and the value embedding for all the same things. We call that in the original attention in the lecture 14, we always analyze what is the query here, what is the value here, what is the key here. We've done that many times, right? Because all of them, or some of them were different. Sometimes key and value were the same, but sometimes it was different. At least query was always different from the keys. But here, we used all the same things. And that's why we call this self-attention. So the same set of words is mapped to query and key and value. So this 3, this vector with size 3 is the query vector for the word come. And the next 3 is a query vector for the word here. And the same, come here and come here. So we have query, key, value representation for each of the words or tokens in the input sequence. Okay? So at the beginning, we are just randomly initializing these W's. So it is also just random projection. But once we train the model, these W will be learning how to map the word embedding, the input word embedding, to the query, the smaller embedding, which we are going to serve as query or key or as value. They will be slightly different. So yeah, as those words are encountered during training, these W's will be gradually mapped X to query key value vectors to serve as its own purpose. You may remember what was the purpose of the query, key and value, right? Query is the basis that we're going to compute the similarity with this query to all the candidates with their key embeddings. And then based on that similarity, we averaged the weighted averaged or the value vectors of those candidates. Here, this query will be serving as a query, and this is as a key, and this as a value. But they are representing the same set of words. That's the only difference. So in self-attention, we're going to play with these small vectors, q, k, v, and we're going to do the attention. So in attention, the query is the basis. So we're going to compute the similarity between this q and all the candidate tokens using their key representations. So here, we compute the similarity with this q and all the words as key. And here, because we're using the same sequence for all the QKV, the key vectors will also have the same words for corresponding to this query, right? Suppose we have like 4 words, and the first word is the query, and then the key is for all the 1, 2, 3, 4. So including Q itself. Okay. So all the words as value are weighted summed after the computing the similarity, and then that is called the attention value, same as the regular attention. So what's the meaning of this? Given some query, we compute the similarity to all other words, including itself in the sentence, and combine their word embeddings, their value embeddings, to update its own embeddings. And because we include the Q itself as its candidates, actually that is dominated. So here, as the query Q itself is included in the weighted sum, we output Z, but that's actually very similar to Q. And it was just including some information from other words in the sentence. That's why we are calling this as contextualization. So each word, at the beginning, they are just word embedding, which is pre-trained. And then they update, contextualize with other words observed in the same sentence with some weighted sum and based on the similarity to those words. This is the key of the transformer. You have to understand this. Okay? Good. So that's what we do, self-attention, the most important part. But we call this multi-head attention. Why multi-headed? Basically, some word may mean multiple things in the sentence. Something like this. The sentence is the animal didn't cross the street because it was too. If we don't know the last word, we cannot decide what this it means. The animal didn't cross the street because it was too tired. So we now know that this it actually means this animal. But if this is too narrow, then this it will mean the street, right? So it's just English thing. So we don't know what it is, but we just want our model to actually have the capability that this some word may mean multiple things. So we actually do this thing multiple times with multiple head. So the first head, which is the orange colored here, so it automatically learns that it needs to attend this animal part. And the second part, it learned that this may mean this tired part. So it needs to attend this tired part to figure it out. It's actually mean the animal. So they need both of these two attentions to figure out this is actually the animal. So we do this multiple times. Actually, in their experiment, they did 8 times. So multi-head self-attention, we just repeat this, have 8 times. So each of them will output Z0 to Z7. So this is the output attention value. And then they map it back to original dimensionality of each word. So we call that in the input, the come here, both of those words were embedded to 4 values. So it maps, linearly just maps back to the same size vector. That is here. So this is the summary of this step 2, which is the most important part of this transformer. So here, instead of come here, we have thinking machines, this very short sentence. And each of these 2 words are embedded into 4-dimensional vector here. And we call that as X, the input. And then we map it to query, key, and value for each of those words by multiplying some linear matrix, W0Q, WQ, WK, and WV. And because we are doing the multi-headed self-attention, we do this 8 times, right? Then we actually do the attention for all of these query words, compute the similarity to all the keywords here. Then based on that similarity, we weighted average these value vectors of all the words to update to the Z0. And repeat that for the next query, and we have the output here. And we do that for all of these, just doing the attention. Then the output will look like this, Z0 to Z7. Then concatenate all of these, and then we map it back to the original size, which is this size. So here, we actually multiply this n times, which means these layers are stacked n times. So at the very beginning, we start with the actual input, but in the next layer, the output will go to the first step as its input. So in the next part, we call it R instead of X, above the first floor. Everything else is the same, just the name of the input is different. So far, so good. Probably this is too complex. So please review the paper and this lecture if you are not following. This is super important. OK, so the hardest part is done. Then each of these words goes through another feed-forward network or fully connected layers like this, value and the 2 layers, fully connected layers. But these are not contextualized. Each word just goes through individually to these fully connected layers to update its embeddings. And then the residual connections are added here, the same as the ResNet. Simple idea. OK, and then we, as I told you, we stack these self-attention blocks n times to repeat these contextualization multiple times. And the very last layer outputs the same length sequence. This is important. Always, the output is the same size sentence or the sequence. And each of those words or the tokens are also the same size, which is 4-dimensional in the previous picture. So the last layer outputs the same length sequence of transformed tokens as input, where each of them is also same size contextualized embedding. What is the keyword here? Contextualized. Why do we do this? For each word embedding, we contextualize or update its embedding, reflecting the semantics of other words observed in the same sentence. And the dimensionality is still the same. So it's still the same vector, but just its meaning was updated or transformed. So that's why we call this model as transformer. Once we just run this transformer model, then the sequence of the embeddings are updated, but they're still in the same dimensionality, and only those values were slightly updated, or aggressively updated, depending on the attention values. So that's the transformer encoder. Great. Hope you understood. All right. Then some more minor things. OK, this is more like the dealing with the sequence, but each of these words were computing the relative pairwise relevance and just updated the weighted summed. So unlike the RNNs, the tokens has no concept of order, right? Even though we just changed the order of those input sequence, actually that's still the same, because for each of those words will be served as a query and compute the similarity for all other words, and then sum all of those values, right? So to inject the order information, transformer adds something called positioner encoding in the input. So the same words at the different locations will have the different overall representation because of this. And they use the sinusoidal encoding. So I'm not going to talk all about the details of this, but here, the time step index means the order of the word in the sentence. The first word is 0, and the second word is 1, blah, blah, blah. And the channel index is because we are always inputting the same dimensionality of the embeddings and outputting all the same size embedding as well. We need the same size vector in order to, we can just add these positional encoding. So if that is like, for example, 1024 dimensional vector, then we need the channel size of the same 1024. So they somehow designed this kind of sinusoidal functions to encode. And just remember that depending on the time step index or the word index in the sequence, this positional encoding is always different. It's always unique. And that will be the hints that where this word was used as the first word in the sentence versus like fifth word in the sentence, even though the word itself is the same. So they add the positional encoding here. And that's it. That's the end of the encoder part. We have to decode then, right? So the entire sentence is encoded at the end of the transformer encoder. And now we need to decode them. So it's very similar. So in the decoder, it's basically the sequence to sequence. So the English sentence is given, and we are going to output the French sentence, for example. So they output auto-regressively. So the input is the output sequence generated so far. And that is given here. And then it outputs the next word. And then it repeats, including that, until it meets end of sentence signal. So it consumes the previously generated symbol as additional input with generating the next. And the positional encoding, this is exactly the same as before in the encoder. So here, they are going to go through two attention heads. And the first one, it looks like similar to the encoder case, but it has the term masked. So what does that mean? It's basically the same, multi-head self-attention. But why is it masked? Because we are generating the next words given the previous words generated so far. We don't have any access to the words after that position. So those words should not be used to generate. So in the we have the full sentence, the answer full sentence in the training data, but we have to mask out all the words appearing after the current position. That's we just call as masked. And everything else is the same, just multi-headed self-attention. So that's it. And then it goes to another multi-head attention. And now this is not masked, but we see that these two arrows are coming from the encoder part. Here, self-attention, query key value, all of them were coming from the same word, right? But this part, the query is coming from here, the decoder, but key and value are coming from the encoder part. Why? Let's see that. In this example, we are translating French sentence to English. And so far, we have output the English partial sentence, I am O, and we have to output some next word here. What it should be? We don't know. We have to look into the original French sentence to answer that, right? Otherwise, we have no idea. So they have to attend the embeddings of the French words, which was je suis étudiant. Okay, so we see étudiant here. So it should be the student. Human will solve this problem like that. And this model is also the same. So they need to attend. So here, I emphasize that they are not masked. Actually, we have to look at the entire sentence in the encoder parts to find out what is the proper word here, which is the translation of some words appearing in this encoder sentence. So that's the only difference. And then feed forward is the same as encoder. And this the n times stacked blocks and residual connection, layer normalization, everything is the same as the encoder. And then they have the linear layer to output the probabilities, and then take the softmax to the class scores and to make them a probability. Then, yeah, the ground truth is we have the correct word for that part, for that sentence. So we just update it. So we just generate the loss comparing the actual word and this estimated probabilities, and then that will backpropagate towards the beginning. Are you all connected? Okay. Okay, so as I told you, these are the decoding steps are auto-regressively continued until we have some special token, which is EOS. So once this model believes that this is the end of the sentence, we are done with the translation, then it will output EOS. It is trained to output EOS at the end of the sentence. And okay, and the output sentence may be chosen greedily, which is the argmax of the estimated probability, or it can differ the decision with the top k choices up to that part. Okay, so we are done with the time, so we are stopped here. And in the next lecture, we are going to cover the BERT and the video transformers in the next lecture. Thanks for your attention.